In this video, we'll talk about cylindrical cell geometry and understand how to calculate coated length, coated area, and coated volume, and also take a look at what lies inside a cylindrical cell. So let's jump into the video. So in this video, there'll be a teardown shown of a 18650 cylindrical cell. Credit to Electronics and Computers YouTube channel. We'll browse through or rather skim through this video rather quickly and see the important points. So firstly, step one is to discharge the cell and make sure that it's close to its lower SOC to avoid any safety related hazards. So once we are done with that, we can open up the enclosure and then start tearing it down. Once you tear down the enclosure, you can see inside jelly roll, different layers of jelly roll consisting of anode, cathode, current collectors, separator, and so on. So let's further open it. Now here you can see the terminals, one connected to the side walls, which is negative terminal, and the other one connected to this top cap, which is also known as positive terminal, and it's separated by an insulator from the casing. So both positive and negative terminals, of course, are separated to avoid short circuiting, and this is how you end up getting a cell which has one terminal on the top and the other terminal on the bottom or on the casing. But usually the side casing is again covered with another plastic cap, so you won't be able to get it unless you remove it. Anyway, so moving on, if you further open it, you can start seeing different layers. So now if you further open it, you can see this golden brownish color which represents copper. So copper is one of the current collectors. And then you can see different layers. Now these black color coatings are one of the electrodes, so it can be anode or cathode. And usually there is a current collector on both sides of which you'll have a coating. So basically the current collector, either aluminum or copper, is dipped into the slurry of electrode material, and then that's how you get coating on both the sides. So if you open the jelly roll further, you can see different layers. So on top we have a separator. So this is the first layer, separator, which is used to separate positive and negative electrode. And then you see aluminum foil. You don't see aluminum, which is light gray color, but because on both sides you have a coating of cathode, then you have second separator. In this case, the cathode was NMC. Then you have separator, then followed by second current collector, which is copper. And on both sides of the copper current collector, you have anode coating, which in this case is graphite. So anode can be graphite or a mixture of graphite, silicon, and even other newer chemistries. But this is generally the case. On the other side, for cathode, you can have NMC, NCA, LFP, and so on. But the current collector usually remains the same. So positive current collector, which is having a coating of cathode on both the sides, is usually aluminum. And the negative current collector, which has a layer of anode on both the sides, is usually copper. So this is what lies inside a cylindrical cell. With that, we have the background to understand the calculation. So let's move ahead. So now on the left, you can see 18650 and 21700. What does 18650 and 21700 mean? So you can also call it 18665 and 2170. 18 represents the diameter and 65 represents the height. Similarly, 21 mm diameter and 70 mm height cell is known as a 2170 or 21700 cylindrical cell. And then inside you have the jelly roll with some tolerance or clearance. If you open the jelly roll or if you open the casing, inside you'll see the following layers. You have separator followed by anode, followed by second separator, followed by cathode, and this keeps on repeating because it's a jelly roll, it's rounded. And this basically represents a sandwich. So this is known as a sandwich. This is the repetitive pattern which keeps on repeating to create a jelly roll, right? And then you can see different views of this image. So this is isometric view. If you see a top view, this is what you would see, a spiral, also known as a jelly roll. If you look at sideways, you'll see the following views. So you can see in some cases, or rather in most cases, anode would be coated more as compared to cathode. So there'll be some anode extra length, which is shown here. So now let's look at cathode length calculation. And before that, let's clear out some nomenclature. Now, I understand it might be confusing to keep in memory, like which current collector corresponds to which electrode, what is positive current collector, what is negative current collector or electrode. So let's simplify it. It's hard to remember names. It's hard to remember what is positive, what is negative, but definitely it's easy to remember color. So the only thing you need to remember is color, and rest would be taken care of in this slide. So there are two current collectors, aluminum and copper. We all know copper is golden brownish in color and aluminum is light gray in color. We just have to remember that. So we have aluminum, which is represented in this color coding, and then we have copper here. Just look at the initials of it. So you can see the initial of copper is C and the initial of aluminum is A. So with that being said, just reverse the order and relate it to anode and cathode. So copper C is related to A and aluminum A is related to C. So it's vice versa. C to A to C mapping. So on both sides of a copper current collector, you'll have a anode coating, and anode is also known as negative electrode. So what is negative current collector? It's copper. Similarly, aluminum A is related to C, which is cathode. Cathode is known as positive current collector, is known as positive electrode. So the positive current collector equivalent would be aluminum. So this is how you can simplify things and remember the nomenclature or convention. Now, once this is clear, we can move on to the coated length calculations. So L is one of the parameter which we'll eventually use in calculating coated length. So let's see how L is calculated. L is equals to pi d square minus d square by 4t. Capital D represents the jelly roll outer diameter. Small d represents jelly roll inner diameter. And T is the thickness of the sandwich. Sandwich, as we can recollect from the previous slide, is a basic building block or of the repetitive pattern in a jelly roll. To understand it better, you can see this image. Golden brown color represents copper. On both sides of copper, we have anode, and anode in this case it's graphite. So we have a graphite coating on both the sides. Then we have a separator. Then we have aluminum current collector, on both sides of which we have NMC cathode. And then we have the second separator. And now this building block is repeated over and over again to create a jelly roll. But what is T? T is the thickness of the sandwich, which is a sum of thicknesses of each layer. So we have 2 times the thickness of separator, 2 times the thickness of cathode, 2 times the thickness of anode, and 1 times the thickness of copper and aluminum current collector. So if you sum all these up, you'll end up getting T. So this is how you calculate L. This is step 1. Step 2 is calculating total coated length of anode and cathode separately. Now, to understand this image better, let's first zoom into this jelly roll image. So in this jelly roll, we have 2 conventions. There's one side which is facing outwards, so radially outwards. When we talk about color coding, again, brownish color represents copper, which is anode. So this is anode, and then copper is the anode current collector, and then on both sides we have anode coating. So in short form, I'll call it anode. Brown is anode, gray is cathode. So this layer of anode is facing outwards. This layer of cathode is facing outwards. So these two are the outward facing layers. Similarly, the other two are the inward facing layers, radially inward facing layers. And this is what we see in this image. So in this image, you can see this is facing outwards and this is facing inwards. Now you can see the gray color one, which is cathode, is having a total coated length which is less than what we have for anode. And this is typically true because anode is generally the one which degrades over time faster than the cathode, and you need more of it for sustaining. So you have anode extra length here on both the sides. Along with that, you can see, for example, if you just compare both the cathode grayish layers, on one side it's coated more. So you can see if we draw a line here, this length or this area is the extra coated length of cathode. Similarly, you'll have some extra coated length of anode. On one side you'll have anode more, on the other side would be less. It's just a limitation of the manufacturing process that you might end up getting slight differences. Okay, so with that being said, we can now calculate anode length. It's the sum of length of anode on both the sides, side 1 and side 2. On side 1 it's L, on side 2 it's L minus anode uncoated length. So you end up getting 2L minus L anode uncoated. Similarly, cathode length is equals to length on side 1 plus side 2. Side 1 it's L minus anode extra length, and on side 2 it's L minus anode extra length minus cathode uncoated length. So you end up getting LC equals to 2L minus 2L AE minus LCU. So you get LA, you get LC. This is the total coated length of anode and cathode respectively. Now, once you get length, area is fairly straightforward along with volume. So if you look at anode area is equals to the length calculated in the previous slide times HA, which is the height. So in this image, you can see this represents the height of anode. Similarly, area for cathode would be LC times HC, total coated length of cathode times the height of cathode, which is represented by this number here. And this is how you get area. And finally, for getting volume, we just need to multiply it with the third dimension, which is into the plane of the paper here. And the third dimension is thickness. Thickness of anode multiplied by area will give you volume. And similarly, thickness of cathode multiplied by area of cathode will give you total coated volume. And courtesy to the source for providing such useful images. So I hope this is fairly clear and straightforward. The major challenge is how you effectively calculate length. Once that is done, other two quantities are fairly straightforward. Now, once you get area, you can now calculate what is known as half cell capacities. And how do we use this half cell capacity? That's a different topic which we'll cover in a later video. How half cell capacity end up creating a full cell capacity. So that's an interesting concept. But for now, let's understand what is loading. Loading is known as capacity per unit area. So per unit area of the electrode. So if it's a power dense cell, the loading would be low, which means per unit area there is less charge. So there is more free space, more voids. So the charge can transfer easily, and hence it's able to deliver higher amount of C rates or higher amount of power. On the other hand, energy dense cell is more dense, as the name suggests, and it has a high loading, which means capacity per unit area is high. So these are the typical two types of cells in which is commonly found in the market based on the application. Different OEMs select one of the two. So if you want more acceleration, if you want to deliver current quickly, then you go for a power dense cell. If you want higher range, you want the battery to last longer, then you go for an energy dense cell. So this is the basic concept behind loading. And then loading would be useful in calculating capacity. Capacity is milliampere hour. Loading was milliampere hour per centimeter square. So we need to multiply it with the coated area to get capacity. And coated area is something we saw in the previous slides. How do we calculate it for a cylindrical cell? So this is how you end up getting capacity. I hope this video was helpful. Thanks for watching.